Thank you everyone for showing up this morning. My name is Alan. I'm the project manager for Team OMUS. I'll introduce the rest of the team here. We have Mohammed Nagibullah, Adrian Alonso, Nick Kelly, Ryan Dale, and Bersin Kalisken here. Mini Sumo Bot, what it is it's two autonomous bots trying to push each other off an arena called a doyo. Okay, the doyo is 70 centimeters in diameter with a 2.5 centimeter boundary. The best of 3 matches wins the competition. The design specifications for our robot is it has to be fully autonomous, can be more than 10 by 10 centimeters, can weigh more than 500 grams, and we had a budget of $500 to work with for this project. In researching winning sumo bots, we knew we wanted 3 key features for our robot. One was a low profile wedge design, 2 is an optimum speed to torque ratio, and 3 is our early opponent detection. As you see here on the right, that's our conceptual design, and to the left, it's our final design. As you can see, we came very near to what our conceptual design is. On our next slide, you can see OMUS 3 in action. It's competing with the RC time constant robot. As you can see, it can easily defeat the robot, and it's a pretty competitive robot.
That's not what I saw in the lab.
Photoshop.
Got the batteries out.
Those are fixed.
Another important aspect of our design is strategy. I'll let Ryan Gill talk more about the strategy.
All right, good morning, everybody. As you can see from the video, we went through all the states of our state machine. To begin the match, we were able to use an infrared remote to start and begin. Once we began the match, we go into our 3 main states, which are the search, the attack, and then the stay-in modes. Within the search mode, we're looking for a target using our proximity sensors. And once we lock on the front sensor, we're going to go into the attack mode where we're going to ramp up the speed to try to push the opponent out of the ring. And then at any point in time, if we hit the boundary line, the white line, we're going to hit an interrupt in our microcontroller that's going to set us into the stay-in mode, where we're going to course correct to try to turn around and remain within the ring. I'm going to pass it back to Alan here to talk about our motors and wheels.
So we know we wanted our robot to be fast, so we chose motors for its speed. We went with the Plulu 75 to 1 gear ratio motors. At 11 volts, this motor gives us an RPM of 800. And with the diameter of the wheels and the motors, we were able to achieve a linear speed of over a meter per second. The wheels were chosen because of its traction. The outer part of the wheels are made out of 820 polyurethane, a very sticky material, and the rims are made out of brass. Because the rims are made out of brass, we were able to put most of the weight of the robot itself directly on the wheels, giving us maximum traction. And to control the robot, I'll pass it on to Adrian. He'll talk more about the sensors.
Good morning, everyone. My name is Adrian. I was the guy in charge of the sensors for Team OMUS. So here you guys can see is our robot, and currently we're equipped with 2 types of sensors. We have the proximity infrared sensor, and we also have the light reflectance sensor. Here on the right side, you can see our final design. We have 4 of those proximity sensors on the top chassis, 1 on each side, and then also we have 4 of these light reflectance sensors below on the bottom, which you guys can see preview here. So going more into detail, what is exactly an infrared sensor? How does it work? An infrared sensor. An infrared sensor has 2 components. It has a transmitter and has a receiver. What it basically does is it transmits a signal or infrared light towards the target, and as the signal bounces off the target, as the signal bounces off the target, the reflection angle is then determined. As the target approaches towards the sensor, the corresponding voltage is then read due to the change in the reflectance of the angle. So exactly why do we use this particular sharp infrared sensor? Well, we want to utilize a sensor that would work in conjunction with the speed of our motors. And we want to be able to have the most capable, we want to be able to have it work in conjunction at the highest capability as possible. So we characterized the sensors looking for three characteristic traits. We wanted the sensors to have a high response time. We wanted it to have an advantageous range, as well as it being accurate and having a linear output so that determining the logic would be a lot more easier. So here on the diagram, we have the dial, and you see these red cones. These red cones are the proximity areas, or areas that the sensor can detect an object. Though you can see that there's a lot of blind spots here in the corners, and we only have 4 sensors here on each side. No worries on our end, because due to the fact of our motors in conjunction with the fast sensors and response times, as well as the range of the sensors, we can easily maneuver around and quickly cover those areas. And here you can see how I exactly characterize the sensor from 0 to 150 centimeters, ranging from 2.3 volts to 0.7, where anything below 0.7 would be determined as no detection. So moving on to the second type of sensors is the light reflective sensors. Here you can see on the bottom, I have highlighted 4, 2 on the back and 2 on the bottom, in the front bottom of the ramp. So what is exactly a light reflective sensor? Well, it's pretty much similar to a proximity infrared sensor, but rather than measuring the angle of reflectance due to the output or due to the target being close to the sensor, we actually measure the intensity of the light. The Doyo has 2 colors of our concern. It has a bright surface and a dark surface, more so white and black. And we're using the analog outputs as digital high and low reading values for our logic input. So a bright surface would reflect more light, therefore higher voltage, and a darker surface, in our case, would reflect less and therefore lower amount. Now I'll go ahead and hand it off to Nick, who will go ahead and explain more further about the microcontroller and how exactly we tie in all these components to our ability.
Good morning, everyone. My name is Nick, and it was my job to make sure that we had the perfect MCU or microcontrolling unit for our robot. Now, there are a lot of microcontrollers out there that could have been used for our design, but we didn't want one that was too overkill, and we didn't want one that was just where we had to integrate external parts into our design. And so we narrowed it down with 2 basic criteria, which was the analog to digital converter that had enough analog inputs for our sensors, and then the pulse width modulation which had enough outputs for our motor drive. And so right here, this is a brief overview of the PIC32 that we chose and how it interacts with all of our devices. You can see that right here, it takes in, it's constantly scanning values read from the sensors, and then depending on those values, we will dictate the PWM speed and the direction of the motors by sending those signals to these single brush motors. Now I'll go back to the analog to digital conversion. Now, since we didn't want anything with too much overkill, the PIC that we chose had 10 analog inputs, and out of those 10 inputs, we are utilizing 8 of those. And of those 8, we have our analog to digital converter set to automatic scan mode, where each channel will scan at approximately 2.7 microseconds. If you multiply that by 8, that's roughly 22 microseconds refresh rate for all of our sensors, which falls well in the time of the refresh rate of the reflectance sensors, which are 3 milliseconds, and the proximity sensors, which are 16 milliseconds. And then once we get these values from the ADC, those values will dictate the PWM, which will dictate the speed and the direction of our bot, which basically it takes the average voltage over a set period, which if we determine that period, we can scale those values to a percentage, which will drive our motor and the direction of where we want to go. And each of these PWM signals will be split in between the 4 motor drivers, 2 on each, or 1 PWM signal for each side of our robot. And then next I'll pass it off to Mohammed, who will go over the PCB layout and power distribution for the bot.
Morning, guys. My first task was to power everything on, make sure everything gets correct power and current. So we looked at the current of all the sensors and the microcontrollers. As you can see here, there's a table of the max current that's being drawn from each thing. What I mean by max current is when it's working at max capacity. And as you can see here, the PIC doesn't use as much as the reflective sensors or the motors. And the motors are the ones that draw the most, 6.4 amps, which is a lot. Usually that only happens if we're holding down the motors at full load, and that will cause it to draw. And that will not happen in a ring. So we wanted to pick a battery that's small to fit into our small design. So as you saw in the video, the matches last between 5, 10, 15 seconds, and we need to have 3 matches. So to do that, we calculated the current and the battery we need, and we found the smallest battery we can find with a 360 milliamperes battery. This will last us about 3 minutes of the match going at max current. Realistically, we are not going to be running on max current. We determined it runs about 15 to 20 minutes per battery, and we also have another battery on standby in case we need to switch up. However, we do have plenty of time with these batteries, and they're very sufficient. The next we need to look at is the voltage of our circuit. So we had different type of voltage. We had first the PIC, which was running at 3.3, and the sensors running at 5, and then finally the motors are running at 11.1 volts. However, since we wanted to have a much smaller design, we wanted to eliminate as much components as we can as possible. So we looked at the sensors and we saw, let's see if we can run them at a 3.3 rather than running at 5. That way we can run the PIC and the sensors on the same voltage, and we would only have to use 1 LDO rather than use 2. So after some testing, we found we can use these sensors, fully utilize them at 3.3, and they work perfectly the way we wanted them. So we dropped them down to 3.3, and now we need 1 LDO, and that would made our system so much smaller, where we can fit everything on one very small board within our design. This will bring us to the final PCB design of the circuit. As you can see, it's much smaller than the 2-layer that we had in OMUS 2, and we have the PIC at the bottom. It uses SOIC package. It's about 300 mil, and then it's very small compared to the socket ones. This is about 1/3 of the size. It allowed me to put much more components on the board, about 4 motor drivers, the LDO and switch and motor. It made our design much more smaller. We're able to stay on the ground and have stronger butt. So now I'll be passing out to Bruce to be talking about the budget.
Hi, good morning everyone. This is Burçin. So I'm responsible for the budget control and the ordering part for our project. So we have $500 limit throughout the semester. As you see here, motor and motor drivers 43% from our budget, and sensors are 32%. Those are the most expensive parts for our design. And also throughout the semester, we did not only build 1 robot, we did 2 fully working robots. And if anyone wants to build one of the robots that we did, it costs $179.99. So I'm going to pass it out to Alan. Ryan, he's going to talk about the project timeline.
So as you can see here, we have a graphical representation of our project timeline. Along the top, you can see our prototypes throughout the semester, and then just below it is our actual built versions of the robots. Also, we have included here at the bottom the milestones that we've accomplished throughout the semester, assembling the robot, finding a target, things like that. The next one that's coming up is our, excuse me, is to defeat Robo Ronin in a competition coming up on the 10th. And you can come see us. Make sure to come there. It's going to be in the engineering building, room 217, from 1 o'clock to 2 o'clock. And then also we're going to be at Design Day on Friday the 11th, and that's also from 1 to 3. Here's a flyer of our robots and the competition showdown. And we actually have a scrimmage match when we were competing against our competition. All right, thank you everybody.